This is the story of the three little pigs and their adventures. Once upon a time, there were three little pigs, and these three little pigs were brothers. The oldest pig was named John, the middle pig was named Dave, and the youngest pig was named James. John was an industrialist, James was an environmentalist, and Dave was a bum. When the time came for each of these boys to leave the farm and start their own lives, their mother gave the pigs a map in which they could build their new homes. Being especially protective, their mother gave them a plot of land protected by a stone wall that curved around a river. And in this case, our stone wall is represented by our equation y equals negative x squared plus 75. And that way, the wolves that lived in the forest beyond the stone wall would never be able to reach John, James, and Dave. In order to determine the amount of land that their mother gave them, the three little pigs utilized Riemann's sum, finding the area under the curve of the stone wall. So in this case, we're going to have an interval of 2, and we're going to use the left bound. So we're going to start on the left side of the graph for 2 intervals. And then we're going to make another box that touches the left side of our box. Repeat that. Now, in doing only the left bound of Riemann's sum, there is a lot of error, but it's an easy way to approximate the area under a curved graph. So now we have to calculate the area of each one of these boxes. And if we start on our left, that is 0, because it doesn't have any area. The second box, since our interval is 2, it's 2 times 25, which is 50. Our third would be 2 times 50, which is 100. And we do that for each box, calculating the area. So we're going to have 0 plus 50 plus 100 plus 130 plus 150 plus 140 plus 100 plus 50 plus 20. Now the sum of this is 860. But we've got to remember our units, and that's going to be miles squared. So 860 miles squared represents the territory in which the pigs can build their house, which leads us to the next part of the story.
For the three little pigs, there is one problem. The main food source that existed was centered throughout the middle of the territory. Still seeking independence, John, James, and Dave decided to build each of their farms as far away from the others, while still maximizing this food source. So, in order to find out the maximum area of the triangle that would surround the food source, the pigs took out pencil and paper and used calculus once again. Okay, so the pigs now know where they're going to stay. They're staying in this territory. And this territory is represented by this parabolic stone wall that surrounds them. And in this stone wall, we know now that there's a food source. And this food source is located somewhere near the middle. So we can be somewhat vague. We don't exactly know where, but it's somewhere around here. It's not in the extreme portions. It's not in the extreme ends of this parabola. So it would be ideal then, with the intention of being independent, with the pigs' intention of being independent, to be as far away from each other as possible while still maximizing the food source, while still being able to share this food source that exists in the middle, and each having a plot of land with enough of it. Now, if we think about this, the best way for them to do this would be to form a sort of triangle, something like this, where each pig in each respective corner of the triangle has their own plot of food source. It has this area, their own area of food source, in which they can grow their food while still maintaining independence and being far away as possible from the others. Now this is what we call an optimization problem. We're finding optimal values of the base, which, as we'll see in a bit, is this value, and the height, which is, as we'll see in a bit, this value. Now, these optimal values, what we're trying to do is we're trying to maximize the size of the triangle, the area of the triangle, while still keeping the triangle in the middle, which is essentially why it's a triangle. So these are really cool. They're really reality-based because, as you can see, we can use it in real life. Now, the first step of these problems is usually the most tricky, and that is to find an equation that pairs the two variables, which in this case are base and height, and it needs to incorporate them, but there's another step after that, and I'll show you that in a second. Now, as we know, in the area of a triangle equals 1/2 of a triangle equals 1/2 base times height. Oops, times height. Now we have this. We have a triangle, and we have base, and we have height. However, base and height are two different variables. They're two different variables that, if those are what we have, we can't solve for either of them. So we need to make this so that both base and height are variables that are similar. So we need to put one of them in terms of the other, either base in terms of height or height in terms of base. Now, if we look at them, it'll be clear to us which of them we want to use. So base, we're going to give this, we're going to say this is the base right here. We're going to make this value x and then this value x divided by the y-axis. And you'll see why we do this. So base equals 2x. And now height is dictated by the y-axis, dictated by the y. And that's what it equals, but if we see this, if we look at this, we notice that the triangle always rests upon the curve of the parabola, of the stone wall in which they live. So this is another aspect, another component of the tricky part, and that is putting one of the variables in terms of the other. Now, since we have this graph of negative x squared plus 75, we can use this as our y value. Why? Because, like I said earlier, these points right here are always going to be on the y-axis, or on the parabola, on the function. So this equals negative, so the height equals negative x squared plus 75. And another way to think about this is that this triangle could be anything. It's not necessarily what I drew. It could be that, if that's the maximum value, if that's the optimal value. It doesn't look like it is. Or it could be something like this, if that's the optimal value. Now I'm going to erase these so that we have as much thinking space as possible. Trying to make this a little thicker. Alright, well, that's definitely a temporary fix. I can redo it like that. There we go. Perfect. Okay, so we have these two values now. We have these two values of x that make up this equation. The area of the triangle equals now 1/2 times 2x, which is the base. We'll move this over, times negative x squared plus 75. Alright, I'm going to rewrite this a little bit. So hopefully you're taking notes, but rewritten, this looks like this. So area equals 1/2 x, or 1/2 2x, sorry, times negative x squared plus 75. Now we want to make this, we want to simplify this. So a, if you might have noticed, simplifies to 1/2 times 2 equals 1. So x times negative x squared plus 75. Alright, so now we're going to FOIL, simple algebra. A equals negative x cubed plus 75x. Alright, so this right here is a very important function. This is our area function for this triangle currently. Now, this is not to say our optimal area. This is not it yet. We still need to find the value of this x. And now I'm going to show you a way to do that. And it's using something called the derivative. Okay, so starting on a fresh slate. The area equals negative x cubed plus 75x. Now the derivative is at a point. It's a concept that represents most of calculus. So at any point on a given graph or table or function, the derivative of a point is the slope at that point. So if you have, so say we have this negative x cubed. The graph of this would look something like this. Now, on this graph, say we're looking to find a point right here, the derivative of that point. The slope of that, if we're draw a tangent line or a line that touches that point at only one point, will look something like that. That tangent line, the slope of it, equals the derivative of that point. So the slope looks something, let's say the slope equals negative 3. Alright, so it's not a terribly complex concept. So now, in relation to these optimization problems, and this problem specifically, this negative x to the third graph, if we're trying to find the optimal values. We're trying to find the maximum area of this triangle, the maximum value of this x. So if this is the graph right here, then at this point, this would be a local maximum, this would be a local minimum, and what we want is to find the x value at that local maximum. So, like I said earlier, what we would do is find the slope at that point. And the slope at that point, if we were to draw a tangent line, is 0. So, on the derivative graph, if we were to draw a derivative graph, it would look something like this. The slope before this point is positive, so it would be up in the positive range. The slope at that point is 0, so it would cross the x-axis, and the slope after that point is negative, so it would be negative underneath the x-axis. And this would look like that. So because at that point, at this maximum point, the derivative graph equals 0, it's very important to find the derivative in this problem, because if we find the derivative and set it equal to 0, we can find at the x value, at where the x value, at the x value in which the y value equals 0. So when, right here, when the y value equals 0, because of the maximum value in the original function, we can find the maximum value, the maximum x value. Now that I've sort of explained the reasoning behind finding the derivative by hand, I'm going to start a new slide, and we're going to work on this, and we're going to practice some skills.